In this example, we're going to apply the power triangle to solve for the phasor current I. So what do we know? We know the phasor voltage is 1,414 volts at a phase angle of 30 degrees. We have two impedances in parallel, and we have what else is known is that for load A we have a power of 10 kVA and a power factor of 0.5 leading, and then for load B we have a real power of 5 kilowatts with a power factor of 0.7 lagging. Okay, so how are we going to solve this problem? Okay, if you want to take a shot at it, do it now. Otherwise, I will start with the solution. So, what we're going to do is use the information about the loads to find the complex power phasor. So, we have our basic equation here for the complex power. And what do we know? Well, we know the voltage phasor. We want to find the current, but we have to be careful because this expression gives that current in terms of the complex conjugate. And if we were to know S, then we could find the current. We could solve for the current. Now, what else we know is we have some partial information about power. Okay, and what we're going to do is we're going to solve for the individual powers, and then we're going to construct the expression for the complex power phasor, and then we're going to plug it back into here and then solve for the current. So that's a basic approach we're going to take. So now let's start solving. Okay, so what is it that we know about load A? We know that load A has a power of 10 kVA, and that is units of apparent power. Okay, and there is a power factor of 0.5 leading. And the power factor is cos of the power angle of load A. So that's why we've denoted theta A here. So that's the power angle associated with load A. And we know the definition of power angle is the phase angle of the voltage minus the phase angle of the current, and that's for that load specifically. The other piece of information we know is that the power factor is leading, so we know that the load A is capacitive. Okay, and we also know that theta A must be negative if it's leading, if it has a leading power factor. So now, to continue, let's just show the power triangle that applies in this case. So we know the apparent power, okay, and we're going to find the real power and the reactive power. Okay, so that's going to be our approach in the next slide. So up here I'm reproducing the information, so that's the same thing that we saw on the previous slide. So what we're going to do is find the real power PA. Okay, so we know that the power factor is cos theta A, and that's equal to 0.5. And then we can say that the real power is the apparent power times cos theta A. So we already know these numbers, and so the apparent power is 10,000, and the cos theta, which is the power factor, is 0.5. We don't have to worry about whether the angle is positive or negative. Sorry. We don't need to worry about whether the power is positive or negative because this is real power and it's always positive. Okay, so that's why we didn't have to find whether theta A was positive or negative. Okay, we just used the power factor directly. So then, let's find the reactive power. Okay, so then the reactive power, we know the expression for it, and that's Q is equal to the apparent power times the sine of the power angle. But now this time, we have to find the power angle theta A, and we know it's negative. Okay, so the power factor is equal to the cos of the power angle. So if we take the inverse cosine of the power factor, which is 0.5, we're going to get power angle. And we know, because since the power factor is leading, that theta A must be negative, and so then we can get our result when we take the inverse cosine, and it's going to be minus 60 degrees. Okay, so then we'll use our equation, okay, to calculate the reactive power, and when we plug in the numbers, we have 10,000 times the sine of minus 60 degrees, giving us the reactive power of minus 8.66 kilovars. Okay, so that is how we solved for the apparent power for load A. So then, what about load B? So what is it that we know about load B? So we were given that load B had a real power of 5 kilowatts. Okay, and we have a power factor of 0.7 lagging. Okay, so when it's lagging, we know that load B is inductive and that power angle must be positive. Okay, and we have our power triangle shown here, so we know the power, and we have partial information right now about the phase angle. So let's go ahead and solve. So now we're getting the components of the complex power phasor, and we don't need to know the apparent power, and we've been given the real power, so all we need to do is find the reactive power. So that's what we're going to be solving for. To solve, what we can do to solve for QB, we can use some trigonometry and say use the tangent of the power angle and the adjacent side to find QB. So it's QB is equal to PB times the tangent of QB. Okay, so it's just trigonometry. We didn't see this equation before, but we can easily come up with it just knowing the relationships. Okay, so let us start solving. So then we know that the power factor, which is 0.7, okay, and that is the cos of the power angle, QB. And so if we take the inverse cosine of 0.7, we're going to get the phase angle, and we know that it must be positive because the load had a power factor that was lagging. Okay, and then when we solve, we get the power angle as equal to positive 45.57 degrees. And then we can use the equation that we've developed, right, with the tangent, plug in the numbers. So we had 5,000 for the real power, and we're taking the tan of 45.57 degrees, which is the power angle, and we come up with the reactive power QB is equal to 5.101 kilovars, and that's the reactive power. So now what's our next step? So what have we found? We've found the powers for each of the loads, okay, in terms of real power and reactive power. So for real power, we're going to add up the real powers for load A and load B, and then for the reactive power, we're going to add up the reactive powers for load A and load B. Okay, so then for real power, we had 5,000 watts plus 5,000 watts is equal to 10,000 watts. And then for the reactive power, these are the values that we found. And then so our final is a reactive power of minus 3.559 kilivars. And then we can combine these two because these are in rectangular coordinates. We have the real power is 10,000, and then the reactive power, it's negative, so we have a negative j, so it lies on the this component lies on the negative imaginary axis, and its value is 3,559 vars. Okay, so, and this, of course, the units of the complex power phasor is in terms of VAs, and that's apparent power. Okay, so then we can write it in phasor form, because we need to solve for the phasor current, and we need to do our manipulations in polar form to make it easier for ourselves, and because our voltage is also given in terms of polar form, and when we do our arithmetic we're going to have to divide, so we're going to make it simpler for ourselves. So converting rectangular to polar, we calculate the magnitude first. Okay, so that's just Pythagoras, and then we take the tangent, okay, measuring from the positive real axis, and then we get a result of 10,610 as a magnitude and a phase angle of minus 19.59 degrees for the complex phasor in polar form. And then we can use the equation that we had originally for the complex power phasor, 1/2 times the phasor voltage times the complex conjugate of the phasor current. Okay, and then when we arrange to solve for the complex conjugate of the current phasor, we get the power divided by 1/2 times the voltage. Okay, so then when we plug in our numbers, we plug in the power phasor, complex power phasor, and then the phasor voltage, which was given to us. Okay, and then we have our multiplier by 1/2, and then we get a value of magnitude 15 for the current, and the phase angle, which works out to minus 49.59 degrees. Okay, so however, problem is we're stuck with the complex conjugate of the current phasor, so we need to convert the complex conjugate to the current that we're going to use, and all we have to do is flip the sign on the phase angle. So what we've done is we've flipped the sign from negative to positive, so then our current is 15 amps at a phase angle of 49.59 degrees. So let's put in the amps there. Okay, so that is an example of using the power triangle.